So this class is Theory of Computation and Programming Languages. My name is Ghassan Shobaki. I will be the instructor for this class. So in the first lecture, what I do in the first lecture is that I go through the syllabus. But before I go through the syllabus, I just give an overview of what this class is all about, what the topics that we will be covering in this class are going to be. Then we go through the syllabus, and then we'll talk about the grading policy and the rules for the class. And I hope that we'll get to finish all of this today, even though it's unlikely. So we may have to use the first half of the second class, Wednesday's class, to finish up the rules. Maybe we can talk about grading today, but the other rules, we'll talk about them next time. Now, theory of computation. So this is a theory class. Now, there are different philosophies in teaching this class, and my philosophy in teaching this class will emphasize theory as opposed to practice, or in computer science, practice is programming. Right? So it's there is theory and there is practice. And how many people think that theory is useless? How many people think that theory is irrelevant? So be honest. Yeah.
Theory is kind of like the rules of the practice.
Okay, yeah, so you will have no practice if there is no theory. So theory, practice is an application. You apply some of the theory, some of the theoretical concepts. So in fact, if you have no theory, there will be no intelligent application. Not in computer science, but in all different fields. So the theory of today can be turned into some applications in the future that we can't even think of. Right? So, for example, to be concrete, the technology that we are using and enjoying today is based on the theory that was developed hundreds or even thousands of years ago. For example, hundreds of years ago, people started studying atomic theory. When some scientists started studying atomic theory, that was pure theory. The motivation back then was understanding the structure of matter. That's what drove scientists to study atomic theory. They just wanted to understand the world that they live in greater detail, wanted to learn more about the world that they live in. And at that point, there were people who thought that, oh, this is theory. Why should this matter? I mean, it's not something that I'm going to use in my job. There were no applications for atomic theory back then when it started. Nobody had an application for that, and it was just pure knowledge, pure science. And many people thought that it's useless and irrelevant because it had no applications back then. Today, all the electronic devices that we are using, and we can't imagine living without, are based on atomic theory. So the theory that is developed at some point may have applications in the future that people who develop the theory cannot even imagine or think of. The pioneers of atomic theory never imagined that people hundreds of years later are going to come up with the idea of electronic devices and controlling the electron and doing all of these electronic devices that nowadays we can't imagine living without. Right? So that's why theory is important. Now when we are doing an academic degree, I strongly believe that when you do an academic degree, you must do you must learn some theory. It's not all about practice. We keep talking about practice and practical things and hands-on experience. I'm not against hands-on experience. I'm not against it. But I don't think that the whole curriculum should be about hands-on. So, in this course, I will emphasize theory, but it will not be totally theoretical and totally abstract. I will try to balance it. I will try to give some reasonable amount of theory, some reasonable amount of mathematical abstraction, okay, a reasonable amount. So it's not going to be a pure math course. It's not going to be completely abstract, completely mathematical, but there will be some math and there will be some abstraction. The amount of abstraction that I feel is appropriate for this class, for computer science students, the amount of abstraction that I feel is reasonable. Okay. Now, maybe after what I have just said, some people may think that what we will be studying in this course has no applications today. Is that true? Okay, so it's not true. Why not? What are the applications of the theory of computation that we will be studying in this course?
Email?
Email?
How they select what is spam?
Theory of computation. Well, see, theory of computation is one of the foundations of computer science, and in fact, you can think of it as the foundation of, as being indirectly used in any computer program. But what I'm referring to here are the direct applications of theory of computation. So, computer science, the foundations of computer science are data structures, algorithms, and theory of computation. Everything in computer science is built on top of these. So you can think of any computer program as being at least conceptually or indirectly built on data structures, algorithms, and theory of computation. But can you give me a direct application of theory of computation? What do we study in theory of computation? Does anyone know what we study in theory of computation? So what we will be studying in this course are...
Like how we use the binary computation?
No, we'll be studying finite automata. Anyone familiar with finite automata? Yeah. So only one person is familiar with finite automata. Are finite automata covered in CC 28?
I want to say it's 28.
28. Finite automata. How many people had finite automata in CC 28?
Well, I think I took that one equivalent at Sierra.
Okay, so how many people have had it here? CC 28 here at Sac State. So were finite automata covered? No? Oh, so,
Can you give me an example?
well, it's, okay, so a finite automaton looks like this.
It's like point A to point B. No, point A to
Yeah,
point B
so-
to point A.
Yeah, recognizing,
You can't circle back.
well, you can circle, but we're not going to get into any details. In the first lecture, I try to avoid getting into any technical details. I like to keep the first lecture on a very high level and to explain what the course is going to be all about. So without getting into much detail. So it's, have you seen something like this with 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1,
So
Something like this.
Yeah.
Like a state machine?
Okay, so you know what it looks like, but you don't know that it's called a finite automaton? So you forgot the name, finite automaton?
We called it like a state machine or something like that.
Or a state machine. Okay, some people call it a state machine. Yeah, a finite state machine. So it's called a finite. Okay, the singular is finite automaton. The plural is automata. And please don't say automatas. Some people say automatas because that's the plural of a plural. I don't like this because we'll be talking about grammar in this course. Grammar for programming languages. And grammar for programming languages is also related to grammar for human languages or natural languages. And in fact, that's something that got me interested in this field. Is that I was interested in linguistics and in grammar. So in this course we'll try to be as precise as possible and as correct as possible. So the singular is automaton and the plural is automata. And there is no automatas. Even sometimes the automatons may be an acceptable plural, but I don't like it. The automata is I feel that automata is the proper plural. Anyway, so this thing is called the finite automaton or a finite state machine. Finite state machine. So at least you have seen it. I'm not going to try to explain what this is in lecture 0. Now, finite automata are going to be one important topic that we will be talking about here. Another topic is the grammars. Oh, before grammars, regular expressions. How many people have seen regular expressions before? Okay, so it looks like more people remember the name
Linux.
Regular expression, maybe in CC 60 in the okay, so a regular expression, something that has stars in it, like A, B. Well, segment. It depends on what tool you have used. Something with a star. What does the star mean? In regular
For all.
expression. Repeating something. We'll get into the details of this. So there will be finite automata and regular expressions, and there will also be grammars. So grammar is something that you probably have not seen before. You have seen grammars for the English language or other languages, but you have not seen grammars for programming languages. So in this course, we will be studying grammars for grammatical rules for defining the correct syntax for a programming language. So, okay, now when I say this, which program do you think uses these concepts?
All.
Hmm?
Probably all.
Which particular program needs these concepts to be in its construction, to construct that program?
Compiler?
Yeah, the compiler. Yeah, so the biggest application of theory of computation is the compiler. The compiler is the biggest application of theory of computation. So the compiler uses finite automata, regular expressions, and grammars, among other things, to do what? What does a compiler do?
Converts high-level language into machine.
Yeah, exactly. It translates code written in a high-level language. Now, when we say high-level language, we mean a human-like language. Think of ourselves as high-level, and we think of the machine as low-level. So the compiler translates a program written in a high-level language into machine code, and it uses many tools and techniques and algorithms to do that. And among the techniques and tools that it uses are the techniques that we will be studying in this course: finite automata, regular expressions, and grammars. Now, even though we will be studying these techniques in this course, the emphasis of this course is not on compiler construction. It's not on how these techniques can be used to construct a compiler. The emphasis will be on understanding the theory behind these. So that's why it's a theory class. So that's going to be the emphasis. We will not have a programming assignment until after the midterm. So in the first half of the class, there will be no programming assignments. There will be pencil and paper exercises, problem solving, homework assignments. So the class will feel like a math class for the most part, because we will be focusing on the theory. Now, if you are interested in learning how these techniques can be used to construct a compiler, then you are encouraged to take the compiler class. Okay? So, but in this course, we will give a very brief idea about compilers, very brief. I will try to keep it at minimum because this course is not a compiler course. So the objective of this course is not to teach you how to construct a compiler. Teaching you how to construct a compiler is done in the compiler construction class. And I will always refer you to the to my lectures for the compiler class, which are available, so you can check those. If you are interested in learning more about compilers and about learning how these concepts and techniques that we are learning in this course, how they are used to construct a compiler. If you are interested in learning more, you can check my compiler lectures online. But of course, in this class, for exams, for examination purposes, you are responsible only for what we cover in this class. So in the exam, you are responsible only for what we cover in this classroom and for what I write on this board. By the way, I will not distribute any tutorial material, so you need to write notes. It will be important to write notes. Now, the lectures are recorded, but you never know. Sometimes something goes wrong, can go wrong. Some technical problem may cause a lecture to not get recorded. So I've had this problem before, but not in, fortunately, it did not happen in my regular classes, in the standard classes. It happened in some of the extra classes that I give for the students who work with me on research. We've had problems with the recording sometimes, but it did not happen in a regular class. But you never know. It's not something that I control or you control. So don't assume that everything will necessarily get recorded. So if you skip a class, you'll be taking a chance. Okay? So you should attend all classes and you should take notes, because I'm not going to distribute any tutorial materials. You'll be relying on your own notes and on the homework assignments and the solutions to the homework assignments that I will be posting. Somebody had a question? No, yeah.
Oh, with the videos where you were going to post them?
On MediaSite.
On the
So,
media.
MediaSite. So they will be available.
Oh, you're going to link it. Okay.
Yeah, so there will be a link to the MediaSite. Whether they will go on YouTube or not, it's something that will be determined later. Yes.
For the exams, are you going to have practice exams?
Yeah, that's an excellent question. So normally, in my classes, I would distribute past exams, and I would go through them in the review session that I did before the major tests, even before the quizzes. I do a review session. Now, this is the first time I teach the course here. I taught it elsewhere, and it was a little bit different because I taught it as a theory of computation course without programming languages. So here it's not much different, by the way. So I can I can reuse many of the homework assignments and exam questions that I gave when I taught this course in my previous institution. I will give you samples. So the short answer is that you will get plenty of sample questions, and we will do review sessions in which we will go through some of these questions. Question? Do you have a question? Yeah. Okay. So I will give you sample questions, and we will go through them in class. So you will be prepared for the test. In fact, for this class, the nature of the material requires solving lots of problems and discussing lots of problems in class, because it's a problem-solving class. So you'll see lots of these. And I will give you enough samples before the test. Okay, maybe I should go through the syllabus because it will ask. Oh, I'm not. Okay. So let's. Okay. So some students may think that in college I need to learn only those concepts or those topics that I will be using in my job after I graduate. And this is something that I totally disagree with. If after you graduate, you're going to use a small subset, only a very small subset of what you learn in college. Nobody uses 100% of what they learned in college in their jobs. If you use 20%, if you use 20% of what we teach you in college, that would be great. And what does this mean? I mean, some people are laughing. Maybe when I say that if you use 20% of what we teach you in college, that would be great, does that imply that the 80% that you learn in college but never use in your job is useless? Is it true that the 80% that you will not use in your job and will not turn into dollars is useless?
Not necessarily.
It's not useless. I mean, life is not all about making a living and making money. Making money is part of it. You have to make money. You have to make a living. So if 0% of what we teach you, will be turned into dollars, then it will be useless. What we teach you here is useless. You have to use some of it, but not all of it. If 20% of what I teach you can get a very good job with that and make the big bucks with it, that's good enough. How do you think about the 80%? The 80% is knowledge. Don't think of this 80% that you will not be able to turn into dollars as a loss. This is knowledge. This is a gain. This will make you a more intelligent person. This will make you a more enlightened person. And this will make you, this will actually increase your chances to find a job. Why? Because the market changes. So there are certain jobs that are hot in the market right now. But after you graduate, or 5 years after you graduate, or 10 years after you graduate, the market is going to change. What is hot today may no longer be hot, and vice versa. So we teach you the foundations. We teach you the knowledge, because what may become hot 10 years from now, any field or subject that is not hot today, but may become hot 10 years down the road, that's likely to be based on the foundations that we teach you. So we teach you the foundations. We teach you the the foundations of knowledge that people will use later. So for example, artificial intelligence is very hot today. But when I was in graduate school, I took a neural networks class a long time ago, 1995. Very old. Very old. So 1995, I took a neural networks class, and it was not hot in the market. And it's just I did not even like the class. It was kind of disappointing. I was expecting something different, but it did not meet my expectations. But now it's hot. But what is artificial intelligence based on? It's based on fundamental knowledge that we learn in math. For example, linear algebra. Right? So some people may think of math as something theoretical, useless, irrelevant. No, that's not the case. So, that's why in this class I will try to emphasize theory. I will try to get you to appreciate theory, to enjoy theory as much as possible, because I think some of the topics in this course are fun. So you're trying to come up with a finite automaton or a regular expression or a grammar to represent or recognize a language is going to be fun. So there is a fun part. So I will get you to enjoy theory, which in my mind I think of theory as heavens and practice as earth. So in this course, I'll try to spend as much time. I'll try to get you to spend as much time as possible here in heavens, in this heavenly world. And after you graduate, you're going to descend down to earth.
Because everything's perfect in theory.
And well, it's not
Until
perfection.
practice.
Theory is not about
And it's
perfection, but it's about the concepts that may or may not have applications. Yes, there may be some idealization in theory. Yes, you may be right. So there is idealization, but anyway, I will let you descend to earth after you graduate. So we'll try to spend as much time as possible in heavens in this course. And in fact, programming is an earthly topic. It's not heavenly. So math is heavenly, but programming is earthly. So that's why there will be minimal programming. There will be some programming in this course, but it will be a minimum amount of programming because, in my view, programming is earthly. Okay, so this is my philosophy in teaching this course. Different instructors have different philosophies. So other instructors may emphasize programming. So other instructors may teach it in a more programming-oriented way, and that's their philosophy. And it's we have the principle of academic freedom, right? So in teaching this course, I will be implementing my own philosophy, which puts more emphasis in theory. But if you are very programming-oriented and you hate math, then maybe you may want to consider trying to get into a section where the course is taught in a more programming-oriented way and a less mathematical way. All right, so we still have 10 minutes. So this is my name. This is my office. My office hours are 10 to 11 Monday, 11 to 12 Wednesday, 10 to 11 Friday. How many people have conflicts with all of these times?
Yes.
Oh, you're the lucky girl. Right. So you have conflict with all of them?
Yeah,
So in this case, we can do office hours by appointment. A particularly good time for me to do office hours by appointment is 12 to 1. So that's what I would prefer. But I'm not going to be, I'm not guaranteed to be in the office between 12 and 1. This is something by appointment. So if you tell me that none of these times work for you, none of them works for you, and you would like to see me, then this would be my preference. If even this doesn't work for you, then we'll find some other time. Okay, so, but, don't let the conflict discourage you from coming to office hours. I don't have an official textbook for this class, but I will base my lectures, I'll be basing my lectures on these two texts, Theory of Computation by Sipser and for Formal Languages and Automata by Linz. And you are encouraged to buy or borrow one of these textbooks. So anyway, so in the first 5 weeks, we'll be talking about finite automata, regular expressions. And in the next 5 weeks, weeks from 6 to 10, we'll be talking about grammars. Don't worry about regular languages and context-free languages. We will define these later. But maybe I should just say briefly that languages, by the way, the word language in this course is not going to mean a programming language. And this can be very confusing, particularly confusing because we are at Sac State, we have a course that combines theory of computation and programming languages. So we should distinguish between the concept of a programming language and a formal language. What's a formal language? A formal language is a mathematical concept, which is a set of strings. A language is a set of strings. So this is the formal language. Of course, there will be a lot more on this when we start, actually going through the material. But a formal language is just a set of strings. Now, what's the relation between a formal language and a programming language? This is something that we will understand through the course. But the concept of a formal language can be used in building a compiler to implement a programming language. Briefly. So everything at this point is brief and vague. And don't feel bad if things are vague and do not make sense at this point, because we will go through everything in detail when we get there. Then we will talk about Turing machines and decidability. This is one of the most theoretical topics where we talk about the limits of computation. Not everything not any problem can be solved using computers. So we think of computers as amazing machines that do magic and can do lots of wonderful things, but computers are limited. And not all the problems are solved by computers. In particular, not all problems can have algorithms for solving them. So what's an algorithm? How would you define an algorithm? Yes?
A set of instructions to perform a task.
A set of?
Instructions.
A set of steps for solving a problem. Someone said a recipe. In fact, that's a good definition. Yeah, it's a recipe. It's a step-by-step procedure for solving a problem. And not all computational problems can be solved using algorithms. There are problems for which there is no algorithm. In particular, the problem of analyzing a program. I give you a program, an arbitrary program, and I ask you to write a program that analyzes my program and determines if this program has an infinite loop or not. Or if this is a program and this is the input, will this program have an infinite loop with this input or not? This problem is not solvable. So you cannot come up with an algorithm that will always give you a yes-no answer. There is an infinite loop, there is no infinite loop. And this is just, again, everything in this lecture is high level and brief, but we will learn more details when we get there. Then we will talk about functional programming and logic programming. These are two different paradigms for programming languages. The kind of programming languages that you are familiar with, procedural languages, and object-oriented languages. These are the languages that you are familiar with. So C is a procedural language, Java and C++ are object-oriented languages, but all of these languages are called imperative languages. They're imperative languages in the sense that in these languages, what you do is that you give instructions to the machine on how to solve a problem. There are other programming paradigms that are more declarative. Declarative languages were including functional programming and logic programming. And in functional programming and logic programming, you don't give, your code is not going to look like instructions or statements that will get executed. They will be more like defining what you would like to see or what the solution to the problem will look like. So basically you define the solution. Again, this is vague and it will not make sense until we get there and we study functional programming and show actual examples. But you should know at this point that there are different programming paradigms, including functional and logic programming. Examples of functional programming languages? Have you heard of
For loops.
Lisp? Has anyone heard of Lisp and Schema? So these are functional programming languages. Logic programming languages. Prolog, that's an example of a logic programming language. So these are programming languages that use different paradigms. And in fact, programming languages or different programming languages, different programming language paradigms are normally taught in a separate class. But here we do both theory of computation and programming languages in one class. And the last 3 weeks roughly will be spent on learning something about the different programming language paradigms, including functional and logic programming.